Okay, so hello everybody. So thanks for being here today. So today we will do some magics with Python on CPU. As always, I have to remind you that if you want to join the school on this summer, you can register since a while now. So if you want to attend the school in Annecy, normally we are practically out of places, but normally it should be quite okay. There is no more place in Toulouse. So if you want to join, maybe it will be on remote only. Except if there is another satellite site available here. We start to have a couple of satellite sites also if you want to stay near to your home to follow the school. If you want to participate, to learn and to be a satellite site, we have a trailer to explain that to you.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Gray Scott School 2026, a free advanced summer school on high-performance computing, designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Gray-Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Gray Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Gray Scott School 2026, Europe's leading HPC summer school.
And if you have extra question, please send us a mail. So with for Garroum, for Marie, or for me, and we will be glad to help you on this path. And today we will do some magic with Python, with Alice and with Jean-Marc. So Alice is a research engineer in scientific computing at LUPM, so at Montpellier, and she works on optimization of astrophysics programs for CT experiment mainly. So with a Corsica program, so it's a particle cascade simulation. So it's quite difficult to simulate, in fact, and to optimize on CPU and GPU. And Jean-Marc is a researcher and work as an engineer in ZIF, so the Zwicky Transient Facility. So it's radio astronomy, kind of LOFAR or SKA in the same ID. And today we will present, you will present to us a lot of wizardry with Python. So mainly on CPU for today. The GPU will be next week because of the calendar. Why not? Again, if you have some question, please write them in the chat. We will answer all the questions at the end of the session. And so without further ado, Alice and Jean-Marc, it's up to you.
Thank you, Pierre. So as Pierre said, we are going to present Python for CPU in this webinar. And I will start with a brief presentation of the Python language, which we all know and use, I guess. So as you may know, Python is a very general programming language. It's open source. It's very flexible, and you have a lot of specialized libraries. It's one of the most popular languages, and it's also very used in education and research. And you can use it for machine learning, data analysis, web, software, etc. But we can also use it for scientific computing, and we're going to see in this webinar how to do it. So the principle of Python is a bit different from other languages that you may know, because Python is mostly used as an interpreted language, which means that it's not compiled into machine code like C or Fortran or C++. Instead, you will compile the source code into bytecode, which is an intermediate format, and then this is going to be read and executed line by line by the interpreter. So your Python code is slower than fully compiled code, but it's also more flexible and easier to use. In Python, you have dynamic typing, so you don't have to specify the type of the variable you declare, so it's also very easy to write Python code. And you can use it for imperative, object-oriented, and functional programming. So why is it so different from compiled languages? Is because when it was created in the 1990s, it was made to be a clear and easy to learn language. It was the point of its development. So when it was first published, it was in 1991. But now the major version we all use is the version 3, which was released in 2008. The latest news in Python are the fact that the language has been aiming at concurrency model that is free of the global interpreter lock, the GIL. So we'll see a bit after what this means. So with Python 3.14, which is the latest stable release, you have now official support for a free-threaded mode and a module to use multiple interpreters concurrently. So these are improvements towards having a better performance in Python. So how can we use Python for scientific computing as a language that we want to optimize and to have a good performance? So as you may know, most of the calculation libraries that we use in Python are written in C and compiled, such as numpy, math, etc. And so the only slowdown that you have in execution is when you call them in the Python code. So the very simple way to get fast Python code is to spend most of the computation time using these optimized libraries. You can also use compilers for subsets of the Python language to speed up your code. So we're going to see in this webinar how to use the optimized libraries and how to write fast Python code and how to optimize it for the CPU. And this is going to be an introduction, but in the Gray Scott CPU course in June, you will delve into it a bit more. Before we start with the libraries, so Jean-Marc is going to present NumPy and I'm going to present Numba. I'm just going to present very quickly some tools that may be useful when you want to write optimized Python code. So first of all, when you have a code and you want to identify what is slow and what is fast, so the hotspots of your code, it's good to use a profiler. And in Python, we recommend to use PySpy, which is a sampling profiler for your Python programs. It has a lot of capabilities because it can provide multi-threaded and multi-process code. It can provide native extensions written in C or C++, and you don't have to modify the code that you provide. Useful options that we recommend is to use it in the speedscope format. So on the next slide, you can see an example of a visualization of profiling in speedscope. So you profile with PySpy, you specify the format speedscope, and you open it in the speedscope app. And so you have an interactive profile, and you can visualize very clearly the hotspots of your code. So this is an example of profiler that we recommend. And when you have identified a function in your code that is too slow, and you want to optimize it. A good practice is to benchmark it, which means you time the execution of the function, and when you change this function, you time the execution of the new version and see if there are some differences or not. And so to do this, we recommend to use the time it module, which is a module that provides a simple way to measure the execution time of fragments of your Python code. So for example, a function, and it has a command line interface and a Python interface. And with the command line interface, you automatically determine the number of repetitions to be performed. So you can time very fast snippet of code, because the time it module will time them, for example, 1,000 times for it to be more precise. What we are going to use a lot also in the Python CPU course in Grayscott, in the Grayscott school, is the built-in magic command %timeit that you can use in the Jupyter notebook. And if you write it in your cell, then it will call the time it module on the snippet of code that you have in your cell. So it's very useful. And another tool that we can recommend for your Python code is the Malt memory tracker. So Malt is a tool that was presented by its author Sébastien Vallat in a previous webinar, and now it has some support for Python code. With this memory tracker, you can track some copies that are not useful, because when you have Python code, Python numerical computation libraries can create copies of data, and sometimes it's not useful, especially with large arrays. If you have a lot of copies that you don't really know about, it can degrade your performance. So Malt will tell you where those copies are, and then you can try to remove those unused copies. Okay, so on the next slide, I just want to do a little point on multi-threading and multiprocessing before I leave the floor to Jean-Marc. In Python, it's a bit different than in other languages, because as I said, in Python you have the GIL. So the reference Python interpreter, which is CPython, uses a global interpreter lock, which is called the GIL. So it's a lock that protects all the objects it manipulates against concurrent access. And this prevents multi-threading in Python. So in general, when you want to do parallel computing in Python, you have to fall back on multiprocessing, for example, with the dedicated module multiprocessing that you may know. However, this GIL is released when you call third-party libraries such as numpy, etc. So why is that? It's because, for example, numpy backends make use of threads. So Jean-Marc is going to present you the numpy backends afterwards. So numpy calculations are multi-threaded by default. With Numba, you can also release the GIL by passing an option, no GIL equals true. So when you use those libraries, you don't use the GIL, but the pure Python that you will have in your code will still be locked by this GIL. And one thing that is new is that since Python 3.13, it's possible to build a no-GIL version of Python. And in Python 3.14, it's actually officially supported. So you have a link, Py3 threading, in which they explain to you how to build a no-GIL version of Python and how to use it. And so when you install it, you can enable and disable the GIL at runtime. So you have an environment variable and a command line option. So it's new, but it's officially supported now in Python 3.14, and it's kind of a big improvement, because this GIL has been decreasing the performance of Python code, so it's a good improvement towards performance. Okay, so I think that's all from me. I'm going to leave the floor to Jean-Marc, and he will present you NumPy in detail. So Jean-Marc, it's up to you.
Okay, thanks, Alice. Now I'm going to tell you about the NumPy library. NumPy appeared in 2006. It's now a standard for numerical calculation in Python for the last, for at least 3 qualities. It's a free software. It integrates into a real programming language. It's a clever interface to handle array and fast. It uses efficient low-level library expressed in SIMD instruction like BLAS, LAPLAC. NumPy has over 500 functions covering the following area: term-by-term operation, linear algebra, random generator, fast Fourier transform, element search, sorting, etc. We will present the data structure of NumPy, the notion of universal function. Then we will see 3 techniques to use numpy efficiently: broadcasting, in-place calculation, reduction function, and selection functions. Finally, we will see multi-threading and numerical backend. So I'll start with the numpy data structure. So numpy manipulates 3 data structure: ND array for multidimensional array, matrix vector, and structured array. The elements of ND array have all the same type and are correctly aligned in memory to use SIMD. ND array can represent image, time series, spectra, or another signal. Vector and matrix are close to ND array with fixed dimension, and structured array gaffer heterogeneous ND array with a named column system like Panda frame. It can represent data and metadata in the same structure, like a signal with the date, location, temperature, direction, and so on. With ND array, you can do a term-by-term operation like addition, multiplication, sinus, selection function, reduction function. On matrix and vector, you can apply a specific function for linear algebra, like a matrix product, or a calculation of eigenvalues. As we have seen, ND array has a central concept of NumPy library is defined as a class. So the important attribute is shape, returns a tuple with the number of elements in each dimension. dtype to numpy define is on type, and bytes to know the memory size of array. And for method, the main method are reshape to redefine the dimension signature, as type allow to cast the array to overtype, and copy to return a copy. Universal function, it's a family of functions that share common properties in NumPy, can be applied on 1 or 2 ND array, and output is ND array. Operate element by element. The binary function accepts ND array in different types and applies the same casting rule. The binary function accepts ND array with different dimension if the broadcast rule can be applied. See Caesar. And over 60 universal function defined, like addition, multiplication, subtraction, sinus, square root, power, and so on. What example of function are not universal? It's function around statistic like max, mean, median. All function around shape modification like swap axis, squeeze, reshape. Function around assembly array, vstack, hashtag, stack, concatenate, or logical function like all, any, logical and, logical or function to select and search elements like where or take. So for the next slide, we are going to focus on broadcasting, which is an important concept in NumPy. Start with the out loop definition. Out loop is a loop that is executed most frequently. It is the innermost loop operating mostly on the element of an array. So using Python loops for the out loops will be very slow. So broadcasting concept allowing you to avoid writing Python loops over the element of array. The simplest broadcasting is a multiplication of an array by a scalar. Here you have an example. I define an array and I want to multiply by 10. So NumPy multiplies all elements of the array by 10 without writing an explicit loop. Now let's look at multiplying an array by a vector. Let's take an array of 10 images with size 200 or 300 that we want to calibrate individually with a scalar. So the calibration is represented by an array with 10 value. So try to use the same syntax in the previous slide, coefficient multiply image. So I define image and coef with a random function, and I write the multiplication like in previous slide, and I have an error. The error is value error, operand could do not broadcast together with shape, blah, blah, blah. So to understand this message error, let's look at the broadcasting rule. The first is a dimension element. Numpy compares the dimension of two arrays starting to the right. Secondly, there are two conditions of compatibility of dimension of the same rank. If the two dimensions are equal, there are no problem. Say one of the dimensions is 1, it's stretched, broadcasted, to match to over. Otherwise, numpy writes an error. A simple illustration of broadcasting is the example of editing an array to a vector taken from the numpy definition. You have the figure in the slide. The rightmost dimension is 3 for the array and the vector for the both array. So the broadcasting stretch the vector along the rows to obtain the same dimension of the array. So in a previous example, the dimension 10 of the calibration vector is compared with 300, which is the size of the image. It is not compatible for the broadcasting. So what should we do? The first solution is to return to a loop with a Python loop. Why not? Otherwise, you can use broadcasting. Here we have two solutions. The first is to modify the shape of the image to put 10 to right. The other solution is to modify shape of coefficient, editing two dimensions to have 10 at left. We will write two versions of this free solution, loops, in broadcasting on image, broadcasting on coef vector. We will write two versions, one version outplace and one version in place. So outplace processing are performed on data on data from array, and the result are stored in other array. So it requires memory allocation. In place processing, you perform over the data in the array, and the result are stored in the same array. So in place processing, it's an important concept to master, especially for the iterative algorithm. Allocation and disallocation memory at each iteration can have a significant cost compared to the algorithm CPU cost. So let's see the first solution, naive loop. We start with a copy of image. You write your Python loop and you multiply the image by the coefficient. Here you have the outplace explicit with the copy image. Let's talk about the shape modification. We will modify the shape of the image or image to satisfy the broadcasting. So numpy provides three functions modifying the order of the dimension. Transpose, simply reverse the order of dimension. Swap axis, move axis, answer the axis target and shift the other dimension to left. You have an example in the slide. So now we can write the first the solution 2 with swap axis with outplace version. Since the result must have the same shape as the original table, you must apply the dimension modification a second time. So you can see the function with swap axis solution. the solution is not very readable. And here, coef multiply swap image cause an implicit memory allocation. For the solution 3, we introduce the notion of a new axis. With a 1D array, it's legitimate to able to consider a 1D array like A as a 2D array with a single row. This point of view doesn't require introducing additional data. With numpy, this is possible with the notion of a new axis, which increase ND array by 1 dimension with a single element. The numpy syntax to add this dimension is where you write your array. So you write line, bracket, new axis, comma, 2 points, and bracket. And if you use the shape attribute, you see the array is now 1, 3 instead only 3. There are another function does the same thing, expand dim. So we can write now the solution with new axis. So from shape 10 to shape 10, 1, 1, we need to apply 2 times new axis at right. NumPy provide a shortcut to write this. Instead to write NumPy new axis, you can write simply known. So the function can be write coef bracket 2 points comma none bracket multiply image. This syntax is short and clear. It's a solution we see most of the time. And here, coef multiply image cause implicit memory allocation. Let's look now that the results are the same for the all methods. NumPy provide a function all close to which compare term by term all the elements of the array. So you call the fifth solution, and you take one as reference, and you call the all close function, return a boolean. As we see, the three solution return the same thing. You can define the concept same with 2 parameters for absolute and relative tolerance. The parameters are atol and ertol. A few words about the limitation of broadcasting. You can find this warning in the numpy documentation about the memory consumption of broadcasting. And sometimes it's better to write an algorithm outer loops in Python. So keep this in mind and do your bench with a realistic data size to avoid scaling issue. Else, certainly you can use instead the Numba library presented after numpy. Let's now look at the possibility of in-place computation with numpy. So when you write in Python b equal a, b is a reference of a. There are no copy. It's a Python feature. Now, if you write with numpy syntax, line equal a, where a is a 2D array, a bracket 0, 2 points bracket. Line is example of a view ND array a. There are no copy and there are no duplication of code. It's just like a pointer on the one line of the array. Transpose, function transpose, move axis, swap axis, return a view of the array for the recent numpy version. So you can do broadcasting with this view if necessary. Another classic in-place syntax is plus equal, minus equal, multiply equal, and so on. And at least universe function give a feature for in-place processing. All universal function have as a parameter out to define the output variable. So if the input variable and output variable are the same, the computation are in place. Example with a sinus function, you call sinus for array A, and if you add parameter out equal A, the computation are in place. So now you can write the solution of the calibration problem with in-place version. You can note there are no written instruction because the result of the array modify directly the array image. We have the time of each version of multiplication with a naive version and in a outplace version and in-place version. So the in-place version is always the fastest version. Speed ratio is R12, and the speed ratio between outplace Python loops and in-place broadcast is R14. Here, another type of broadcasting had a vector on each column on an array, as in the figure. Here you have the free outplace version of this computation. So the first is with a loop, the second with a new axis to the vector, and the last to modify the shape of the array, I use transpose with T attribute to transpose the array. Now there are the in-place version as a previous problem. You don't have a return function. The results are almost the same. In-place version is always the fastest version. The speed ratio is between 2 to 3. And here the ratio between outplace Python loops and in-place broadcast is more important, is around 10. Last example with sinus A x plus b in place outplace. There are three versions with 2, 1, and 0 copy. We use the in-place feature of a universal function with parameter out, the last solution, and you have the time of the time for each solution, and you have a speed ratio of 2 between the naive implementation and the in-place implementation. Now let's look at another type of implicit loop that NumPy offers with axis parameter. A reduction is an operation that summarizes several values into one, like a sum, average, max, and so on. NumPy implements this mechanism to iterate through elements to avoid writing a loop with the axis parameters. So axis equal n indicates that the reduction loop is along axis n. The return array, the size along axis n is 1, and by default this axis is squares. Return array lose this axis, and some functions have parameters keep dim to prevent this. So here you have an example of to compute the sum of an array for only a column. So you call a sum with the name of the array and parameter axis 1. And you have the two versions with keep dim or not. So the difference you have a couple of brackets in place. Another area where NumPy provides functionality to avoid writing Python loops is selecting element from an array to make another array. There are two ways. You can use fancy indexing. You can put instead of an index or slicing, an index array, 1D or 2D, or list. And the return value select element in the array. For large array, you can use a function called take on axis. This function is in fact compatible with the output of argx family function like argmin, argmax, argwhere, and you have example. At first, I call argmax with parameter keep dim true, and after I collect the maximum with the function taken on axis with the return of the argument index m. Now we'll talk about multi-threading. So numpy should be considered in two parts. Front-end, it's API Python, and backend, the most used is Blast, Lapack, in C or Fortran. Multi-threading rely only on the backend, since there are several backend solutions, MKL, OpenBlast, Netlib, and several versions of multi-threading NumPy function are not listed in the NumPy documentation. It depends on the backend. For the thread control, you can use the overmount variable associated to the multi-core library, such OpenNP or MKL variable, current variable used for defining the number of threads in your environment. To finish, I present a benchmark between MKL and OpenBlast. So I have three versions of Python and backend, and NumPy 2.2 with OpenBlast, NumPy 1.26 with Intel MKL. At the moment of the bench, MKL is not ready for the numpy version 2. And the last is numpy 1.26 with OpenBlast. So we will compare two backend, so MKL and OpenBlast with two versions of NumPy. On the slide, you have three versions of NumPy MKL tested on Sycl and quad core system. numpy version 2.2 OpenBlast it's a reference with one core. There are C type of tests: FHT, scalar product, polynomial calculation, a log function, cumulative sum, and the search of max. The graph shows the ratio compared to the reference. So there are only 5 bars by operation, with the reference version would be 1. As you can see, only MKL backend take advantage really of multiprocessing. And on the other end, the search of the max with backend is 2 times slower. Else, with one thread, results are almost similar. It's finished for NumPy. I will now hand over to Alice, who will speak about Numba.
Thank you, Jean-Marc. So we're going to finish this presentation with the presentation of the Numba compiler, which is another way of optimizing our Python code. So what is Numba? It's a JIT compiler, so a just-in-time compiler, that will translate your Python and your NumPy codes into optimized machine code. So to do this, it uses the LLVM library, and it can optimize for different architectures, so sequential and multi-threaded CPUs, and also for GPUs. So the gist of Numba is that when you compile your Python programs with Numba, you can approach the performance of C or Fortran code. However, it works best for codes that uses arrays and numpy functions, as well as loops. And the rest is not supported. So if you use another library like pandas or stuff like that, it will not be compilable by Numba. So how does it work? On the next slide, you have a brief overview of how Numba works. So to call Numba, you have to put a decorator above the function that you want to compile. So for example, here we put @jet above the function, the definition of do math function. So for a decorated function, Numba will read the Python bytecode, and it will combine it with some information about the types of the function's input arguments. So here, x, y. It will analyze and it will optimize the code using the LLVM compiler library. And this will generate a machine code version of this function. And this machine code version is going to be adapted to the capabilities of your CPU. Once this is done, so this compiled version is also going to be stored in the cache for subsequent uses of this function. And the next time the function is called, instead of redoing all this process, Numba will just use the cached version and will not have to compile everything all over again. So when you first compile with Numba, it's going to take a bit of time. But then when you reuse the function that has already been compiled, it's going to be much faster. So on the next slide, you have an example of how can we use Numba in our Python code? So to use it, you just add some decorator to the functions or the loops that you want to optimize. So the JIT decorator is the most common, and you have frequently used options that you may see in Numba code. So you have noPython equals true option that we're going to see after what this means. You have parallel equals true to parallelize, so we're going to see after also what this means. And you have fast math equals true. This is to use like optimize the computation of trigonometric functions or stuff like that. So on the next slide, you can see the explanation of this noPython mode. So what does this mean? So when you compile with the JIT decorator, and you choose noPython mode, it will compile the decorated function so that it will run entirely without the involvement of the Python interpreter. So you're going to have the best performance, but you have to have a code that is compilable by Numba. So it's sometimes a bit hard because you have to do some code refactoring, you have to get rid of the libraries that are not supported by Numba, etc. But if you want performance, it's this mode that you have to use. The object mode is the fallback mode. I mean, it was the fallback mode of this noPython mode. So if your compilation in noPython mode fails, Numba will compile using object mode if you set noPython equals false. So in this mode, you will have only loops that will be JIT compiled, and the rest of the code will be run by the interpreter. So you're going to have deteriorated performance with respect to the noPython mode. So it's best to avoid using this mode. In the past, it was a fallback mode if your noPython mode failed in the past. And so if you look at some Numba code from a few years ago, you can see a lot of njit decorators, which is short for JIT noPython equals true. Now you don't have to write it anymore. noPython equals true is the default. So when you compile with JIT, it will try to compile in noPython mode all the time. Another thing that is useful in Numba is its capabilities to multi-thread loops or functions. And it's very simple when it's possible. So if you want to use this automatic parallelization with Numba, you have to specify the option parallel equals true. And if you want to parallelize a for loop, you have a special instruction that is prange, and this will indicate that the loop can be parallelized. So if you type for I in prange instead of for I in range, it will indicate to Numba to parallelize over the values of I. So you have an example just here. It's very simple, but then you have to check that this is actually parallelizable. So once you compile and you multi-thread, what is the performance that you can expect? So first of all, it's very important to specify that Numba, you cannot use it all the time. It's It should be used when you have code that is made up of numpy arrays or loops with numerical algorithms, for example. So it's perfect for scientific calculation, but it's not usable all the time. You can use Numba also to create missing numpy functions. So for example, you have a function that has no equivalent in numpy, but you still want it to be fast. You can compile it with Numba if it's compilable with Numba, and it will be a kind of a handmade numpy version of it. And yeah, as I said, the main limitation is that you can only use it on pure Python or on numpy code. So no other libraries are supported. So it restricts this use. As I said, when you compile with Numba, the first call to the function is going to be the call where the function is going to be compiled. So it's going to be a bit slow. So when you want to measure the performance of the functions that you optimize with Numba, it's better to do a few runs so that you can smooth out the time spent in the first compilation. So with the timeit module that I presented earlier, the number of iterations will allow you to smooth out the time spent during the first iteration. And so in the documentation, they specify that the performance gain that you can expect is around 2 when you compare it with NumPy code. So it's already something good. And of course, if you compare it with native Python, it's going to be much higher, so around 200. But we don't recommend writing native Python. So yeah, you should expect a code that is 2 times faster than your regular Python code with NumPy. Let's check out the last slide here for an example of how this works and the performance that we have. So here we import Numba and NumPy. The first definition of the function go fast, which is it's just a simple function. And then, so we time it, it's 21 microseconds per loop. So with the timeit module, it will do, it says, I think 7 runs. So it did 7 runs of the benchmark to find out kind of a mean of execution time. And then on the cell 14, you compile it with JIT. And when you time it afterwards on the cell 15, what does it tell you? It tells you, first of all, that the first run was much slower than the other runs. This is because it's the run that you have a compilation in, and the other runs will use the machine code that is stored in the cache. And also it tells you that the execution time is now 3 microseconds, so 7 times faster. Yeah, this is how you can easily improve the performance of your code, but with keeping in mind that it's only restricted to some parts of Python, namely numpy arrays, loops, stuff like that. Okay, so that's all for the Numba presentation, and it's also the conclusion of our webinar. So what we can conclude is that Python was developed and popularized for its flexibility and its ease of learning, but not for its performance. However, it's possible to do scientific computing in Python thanks to its vast ecosystem of optimized libraries. The basis of it is to always use NumPy, which is like the basis of vectorization in Python. And also when checking the backend of your NumPy, you can enable further optimization. And when the code lends itself to it, you can use Numba to achieve performance close to that of machine languages. Here you can see some libraries that are NumPy clones for some of them. So this NumPy API was cloned for a number of libraries, notably for GPUs. And this is something we're going to talk about in the next webinar, actually, next Thursday, which is going to be May 7, and it's going to be about how to write Python code for GPU, or how to translate your Python CPU code for GPU. So thank you for listening, and see you next week. And now we have time to answer some questions if you want.
Okay, thank you, Alice and Jean-Marc, for the nice presentation. So we do have some questions already. So a question from Jules: is there a support for fuse multiply add for NumPy in ND array? Or maybe you have to do some Numba wizardry with it?
I'm not sure if backend NumPy recognize some FMA. Maybe equals the right function. I'm not sure.
Yeah,
I don't know either. I don't think I've ever seen it. This fuse multiply add in NumPy.
Okay, so maybe no.
Yeah.
But you can definitely with Numba. So if you are stuck, normally it should be okay.
With Numba, I know you can activate FIME option like this. You have a control of option of compilator optimization.
Okay, so if you really want FMAs, normally with Numba, it's okay. Question from Mathieu. Hello, could we have access to the slide? Yes, normally they will be available this afternoon. Question from Sergey. Oh yeah. With GCC Clang, they can take few seconds to compile or link even on a shortcode. How much time does it take to Numba to compile a shortcode?
So, for example, in the example that we saw on the last slide, it was 7 times slower than the code itself, the execution of the code itself. So it can be a bit slower, but it's not that much. But here the code was particularly simple. I guess there are some examples where you have to wait a bit more, but I don't remember it being a problem in my use of Numba.
Yeah, maybe what I can add also is it's totally normal once you activate a lot of optimization passes on a compiler to have a compilation time of roughly 1 second, because all the compilers, especially G++ and Clang, try to compile a full file in roughly 1 second. So even if you have one function in this file and you ask the compiler to optimize it well, could take 1 second because the compiler knows it has time to optimize. So even with one function of 30 lines, whatever, you can get a compilation time of 1 second. And since Numba split all the kernels into separate files, I guess, you could have this kind of behavior, but it's totally normal. It's up to the compiler. So it's the same problem once you want to optimize the C++ code and you compile, and the compilation takes a bit of time because you ask specific optimization and the compiler enable a lot of passes. So it's totally normal. Question from Jules regarding reduction in parallel with Numba. How does it know which variables are shared by the threads?
Yes, I think it's automatic, so it will infer itself the fact that with the plus equals you have a reduction, and then which variable is going to be shared. I think it's automatic. You don't have to specify it. How does it do it? Yeah, I think it sees this plus equals and then knows that it's going to be a reduction, and then that you're going to have to share the variable by the thread.
Okay, so yeah, maybe if you are used to OpenMP, for example, you know that in the OMP parallel 4 you can specify shared memory for the thread. Maybe here you cannot, or maybe there is a way to if you create a temporary variable inside your kernel, maybe the Numba can figure out that okay, it should be a shared variable. Maybe there is some heuristic for that. Yeah, question from Sergey. Does the code produced by Numba use SIMD?
I think the LLVM it uses SIMD, but then you don't use SIMD yourself when you use Numba. It's going to be under the hood.
Yeah, so normally if everything goes okay, normally you have SIMD, but if the computing is too complex or you don't have enough register or whatever, maybe it's not the case. Is it possible to get the binary somewhere in a temp directory to spy the binary with Macao to be sure that everything was okay and the kernel was written well?
The binary, maybe. I know you can see like some assembly code with Numba. You have an option to print it. The binary, I'm not sure, but maybe.
Yeah, I'm pretty sure there is some hidden directory somewhere with all the binary. So if you really struggle to get performances, maybe you should ask Macao on the compile library directly if you can get them. Would be somewhere hidden in the documentation. Question from Hachel. Big thanks. Would it be possible to get the slides document in order to have time to read them again? Yes, we'll have everything online normally this afternoon or maybe late afternoon. But yeah. Question from Vaik. Is it possible to change the default number of cores that Numba uses? You mentioned it uses all available cores by default. Or maybe you should have a global variable, something like that?
You have an option, I think, set num thread.
Yes, in the API of Numba, yes. You can set the number of core directly without a variable environment.
Okay, it's per kernel or it's globally?
By kernel.
Okay, so yeah, but the point is you can do the same with OpenMP as well. But if you fix the number of threads and you forget it, at some point, if you use a bigger machine, you will not have the performance that you want. So always be careful once you do this kind of stuff, because at some point you could have some trouble with that. At least one of my teachers did have some trouble with that. So yeah, for NumPy, once you use ND array, it's okay. But if you use, for example, H5Py or this kind of stuff, you get records generally. Is it possible to vectorize some records or to transpose them so you get columns with nice values and not a big mess with a really complex type?
You speak about structured array or record in NumPy? Yes. What's
because by default, once you get a record, you have lines with really complex types. And what I would like, if I want to compute some kind of this stuff with Python, is to have columns with one type per column with a named column. Is it possible?
Yes, you can have heterogeneous type in structured array. It's possible. You can have an array of different dimension, only scalar. They accept many types. In fact, there are two versions of structural array with the name colon are a string, and another structure is called a record, I think, when the name of the colon in string become an attribute of the records.
Okay.
But the performance is little slower than structured array with name colon in string.
Okay, so if you can choose, it's better to use ND arrays. Yeah. So in fact, that's also the main point of this presentation. Don't use loops, use arrays and try to express your problem globally and not element by element. And
if possible, in place processing.
Yeah, because of course allocating it's not cheap, even in Python, of course.
Yes.
So you don't want to allocate, of course. That costs a lot. On memory alignment, you said that it's automatic. It's automatic. Last time I checked, it was on 64 bytes, so AVX512. Can you change it, or it's nice default? And
I don't know.
Okay.
Advanced feature, I don't know.
Because for alignment, it's okay. But for example, if I have a big matrix with last dimension, which is quite small, the contiguous dimension, if I get a padding, the padding will be really big, and I will allocate too much memory for what I want to compute. So maybe, or maybe it's because my matrix is not well ordered, and I have to swap axis and to realize the swap to be sure that everything is better. But sometimes you don't have choice.
I don't know if at the numpy level API you can control that, because it's deeply processing by the backend. And in fact, the API numpy don't know what exactly what the backend do.
Okay.
I see the thing like that. Typically, you cannot define, for example, if a numpy function is multi-threaded or not at numpy API level. It's a backend.
That's just to do the backend, and so depending on the number of elements, I guess at some point you will say, okay, I want to split. In fact, slide 42, once you mentioned the performance with the NumPy with MKL, with OpenBLAS. It's really strange to get the MKL a bit slower in max and sum.
Yes.
What is the size of the problem, the number of elements that you used for the computation?
I must open the code to do that.
Because yeah, it's can't happen. Okay. Intel engineers are not perfect, but normally should be quite well optimized. So yeah, it's
max deck.
and maybe yeah, you have another trick also. Once you use MKL, you can also recompile it for your specific CPUs and not get the generic one if you want to get extra performances also. So it's a bit tedious, but if you really need to have best performances possible, you can do that.
The bench with a vector 4 megabyte.
Okay, so you are somewhere in the L3 cache. Yeah, it depends on your CPU because, of course, if the CPU has lots of coring or not, maybe threads can fight at some point. Sebastian will show that in the school.
Mm-hmm.
So sometimes you can start a lot of threads and thread that is fighting in the L3 cache and you don't get performances at all. But it's not the fault of the implementation; it's the fault of the number of threads that you use. So yeah, that's everything. Every time you start to change the number of threads, it's quite tricky. You have to check what you are doing. Oh yeah, once you transpose or you swap axis, normally it's not a real transposition. It's just NumPy figure out that okay, you want to read the array in a different way, but you have to use as contiguous array to be sure that the transposition is effective. So maybe at some point, if you want to transpose, it's better to do it at the very beginning of your simulation, and then you reuse the transpose array, and maybe at the end you transpose the results, just to avoid to be sure that once you compute contiguous element, and the vectorization goes well with your broadcasting, for example, should be better. No.
So when you apply the transpose function, the data are not modified. It's a view. It's a notion of NumPy. It's a pointer of the array. So for when you use a transpose vector, he knows the order of the axis and he adapts the operation to this form. If you really want to transpose the data in memory, I think you must use a copy.
Or you use the as contiguous array, the NumPy as contiguous array function.
Okay.
If you really want to do that, because at some point, maybe I'm pretty sure that people in the chat will try to swap axis and they will not get much performances, and that's because the data are not copied, so are not really shuffled the way you want. So that's a view. It's important to have that in mind also. The problem once you use multi-threading with NumPy, so it depends on the backend, and sometimes you have to use MKL parallel stuff, and sometimes OpenMP parallel stuff, and you have to check. There is no common way to do that in NumPy, and then you will figure out to talk to the backend in a nice way. So because that could be quite tricky if you have a NumPy and you want to change the number of thread, and oh no, it's not the backend I want, so I use all the thread that I don't want.
You can use the function numpy show config, and I think you can find the multi-threading manager.
Yeah, but after that you have to set different variables to command the backend.
Yes, effectively.
Okay, at least you have to. So
you
maybe
must adapt your environment to the thread manager.
But yeah, it could be tricky. You try to force the number of threads, and that nothing is changed, and okay, it's another backend.
Yes, it's
So.
quite a problem of portability to another site.
But maybe it will come at some point. There will be a common API to talk to the backend and say, okay, I want this number of threads maximum and not much. To be sure that to avoid this kind of stuff should be nice. In fact, or maybe you can do yourself, but it's better if it's handled by Numpy itself. Oh yeah, question for Numba. So you at least you mentioned that in Numba you can refactor your code to have better performance and to use the no Python options to be sure that you have only binary, and so you pay the compile time, but at the end it's okay after that. Can I fuse some kernel? Can I have some kernel fusion? Or do I have one little library per kernel, or at some point, if I JIT everyone, Numba will understand that maybe I can have one binary to call it, and not call a kernel, go down to Python, call another kernel, we go down to Python again, and call another kernel. Is it possible?
I don't know actually. When I said refactoring, I said I meant remove the other libraries that you use. For kernels, I don't know.
Okay, so maybe because there are more and more library which get this kind of feature that you can fuse the kernel if you want.
Yeah, I don't know. Sorry.
Jean-Marc, you wanted to add something?
If you call the Numba function in Numba function, the Python part is not called. You stay in a Numba domain.
But if I call several kernels, do I stay in the Numba domain, or do I have to jump again in Python to call the next kernel?
So to do that, you can create a Numba function several core kernel, and you stay in Numba domain.
Okay. So it's okay. It's definitely So it's a bit of work, but you can. So yeah, if you refactor and you say, okay, I have this bunch of kernels to call, and then I create one kernel and I JIT compile this one. If all the other are also JIT compile, I'm pretty sure that if not the case, you will have a problem. But if you do, normally you should have a full part of your computation directly in binary. Okay, it's nice. It's really nice. So yeah, you pay the compilation as for the question of Sergey, but once you are in your kernel, you stay in your big kernel, and normally you get all the result at the end, but no more Python call. And maybe also for the threading, it's better because you don't have to jump in and out and reuse your kernels and your threads and stuff like this. You create your thread once, you reuse them a lot of time, and then you remove them, and it's okay. Okay, it's nice. So yeah, it's again, the design is important. It's really important to add this. And yeah, to reloop with the question of Jules, maybe if I don't have FMAs in NumPy, I can use normally Numba. Normally Numba should figure out if it's possible or not, because depending on your hardware, maybe you don't have enough register or stuff like this can happen. But normally the compiler should help you.
I think there are specific options for FMA with Numba.
Okay, it's not only fast math. You can.
It's different, I think.
Okay, so it's.
The option is like search FMA in the mathematical expression.
So you have an extra research to. Okay, why not? Because yeah, you can forward the option to the compiler, and the compiler will do it for you. So, but okay. Oh yeah, must forgot the first question I had. Since in Python 3.14, if I don't have a GIL, it's supported to don't have a GIL. Do I have real threads available? So I can create a thread with a thread class, or not yet? Because now we use multiprocessing with processes, but at some point we will be able to use thread directly in Python with a shared memory and stuff like that.
So I think that's the goal, but I don't know yet how you manage the threads. I would have to check. You have on the presentation, you have the link to the Pi free-threaded guide, which is kind of official, I think, in which they tell you how to use it. I don't remember seeing anything about how you manage threads.
There are module threading in Python, and the API is close to the multi-processing. Multi-threading module is available in Python for many years, but with one thread at the time before the free threading feature. Yes, you have share memory, lock, all the real-time programming is available in Python.
Okay, so normally we should be able to use it now without performance problem.
Yes, the API
yes.
is ready, but the performance is not here until the no-GIL function.
Yeah, that's a problem. But since they try to remove it, and it's normally official, since you mentioned in 3.14, it should come at some point. We should get some performances with it. But maybe it's also a nice point to get a real backend, and the backend is optimized to have threads and manage the thread well. And it's better because it forces you to think with your design, to do global computation, and not to struggle with the element. So it's nice also to be able to do that. So Jean-Marc, you mentioned in your NumPy implementation that you have the naive way once you want to call a sign or stuff like this, and you can have an advanced way without copy, stuff like this. But if I implement the naive way because I'm not aware of all this stuff, but I use Numba, can I be saved by Numba? Or do I have to explicitly tell that I want to do an in-place call?
I don't know with Numba.
Because naturally I would definitely use the first implementation here, which is a naive one. But if it's slow and I use Numba, maybe Numba will figure out that
yes,
get all my vectors,
yes,
and everything will be faster.
Yes.
But maybe with the out explicit, maybe it will be better. I don't know. We will have to check.
Yeah, to check that.
Okay, so we are just on time. Or maybe you want to add something, Alice, Jean-Marc? You already teased a bit the next week part.
Yeah, just come next week for the GPU part, and thank you for watching.
Okay, thanks, Jules. Okay, we have some thanks in the chat. It's time to stop. So thanks everybody for coming here today to join us on the Python on CPU. So next week we'll do some wizardry with Python on GPU with a lot of technology. I don't want to spoil too much, even if you already did a bit here. So don't hesitate to register to the school. It's really important if you don't want to miss it, especially if you want to attend the school in Annecy or in a satellite site. Have a nice day and see you next week. Bye.
Thank you.
Thank you. Bye.